So we have an equation that describes acceleration. And when you look at this equation, I hope that you would recognize fairly quickly that this acceleration is not constant. Because as time goes on, I multiply in the x direction, my acceleration is multiplied 3 times the time, and in the y direction 4 times the time. So the acceleration is changing. So that tells me I cannot use my equations of motion. I have to rely on my process of taking the derivative of position with respect to time to give me velocity, and taking my derivative of velocity with respect to time to get acceleration. And since they give us the acceleration equation to begin with, that means I'm going to have to work backwards. I'm going to have to ask myself, what equation, when I take the derivative of it, do I get this? Okay? And work backwards from there. What equation do I, when I take the derivative of position, do I get the velocity equation? Okay, so the fancy word for that is integrating. If you haven't taken calculus yet, that is a term that you will become very familiar with. If you've already taken calculus, you know what I'm talking about. Integration is like reverse derivative. Okay, it's working backwards. Okay, so we're going to show you how we do that. So first of all, if you recall, I gave you this sheet early in the semester, how to work physics problems. Write down what is given, write down what you're looking for, figure out the formulas you need to use, the equations you need to use, plug in your numbers and solve it. Okay, so let's take a look at my hand solution here for problem 19. So that's what I've done at the top of the page. I've written down what information is given. They gave me the equation for acceleration, and they told me some information about what's happening at the beginning. At time equals 0, which is the beginning, I know that I'm located, or the particle is located at 20 in the x and 40 in the y, and it's moving with a speed and direction of 5 meters per second in the x and 2 meters per second in the y. So we call these the initial conditions because that's what's happening at the beginning. So that's what's given to me. Then what am I trying to find out? Here it is. At time equals 4 seconds, I want to find out where is the particle located, and I want to know which direction is it traveling in. So I put a note here with a star because it's very important. The acceleration is not constant, so we cannot use the equations of motion. Instead, we're going to integrate the acceleration equation twice. The first time will give us the velocity, and the second time will give us the position. And we work separately in the x and the y directions. You may have noticed in the book they showed you that the derivative of position in the x is the velocity in the x, and the derivative of the position in the y is the velocity in the y. The reason for working separately in the x and the y directions we'll talk more about later, but for now, just know that when we're working with vectors, we're going to work separately in the x and the y directions. Treat them separately. All right, so here we go. In the x direction on the left side of the page, my velocity is the integral, that's the symbol for integral there, of the acceleration equation with respect to time. So it was shown to me that here it is, the acceleration in the x is 3t. So I ask myself, what, when I take the derivative of it, gives me 3t? So I know that it came from something that had a power of 2, because that subtracts by 1 to give me this t to the first power. And I know that when I multiply that power times the coefficient, I need to end up with the number 3. So with a little thinking, you can see that when I multiply 2 by 3/2, I end up with 3. So there's the integral of 3t. But remember, if I had started with this velocity equation and there was some constant here, when I take the derivative of it, that constant would completely disappear. And so there's no way I can know what that number is if this is the only information given to me. But that's not true. They have given me the initial conditions. So with this information right here, I'm going to be able to figure out what that constant number is. So it told me that when t equals 0, the velocity equals 5. in the x direction. So that's what I do. I plug in 5 for velocity in the x, plug in 0 for my time, and now I can solve this equation for c. And I see, that c is equal to 5. Okay, so now I can come up with my complete equation for the velocity in the x, 3/2 t squared plus 5. Then I'm going to do it again in the y direction. My y acceleration was 4t. Again, you can figure out that when you take the derivative of 2t squared, you get 4t. So 2t squared is the integral of 4t. And again, I'm going to apply my initial conditions to figure out what this constant of integration is. That's the name for this constant here that we would not know if it were not for the initial conditions. It tells me at the beginning the velocity in the y was 2, so I plug those values into my equation and solve for the y integration constant, and that is the number 2. So now I have equations for both velocity in the x and velocity in the y, and now I'm going to have to do it again. Okay, I'm going to integrate again to get the expression for my position vector. Now that we're working in 2 or 3 dimensions, we're going to use the letter r for position. When we were working in 1 dimension, it was common to use the letter x if we were working on a horizontal axis, or the letter y if we were working on a vertical axis. But now we have x and y components to our position vector, so we use the letter r. Here we go, work separately in the x and y again. In the x direction, I'm going to integrate my velocity equation that I came up with. So there it is, 3/2 t squared plus 5. And so this one may not be quite as simple to integrate, but it's still the same reasoning. Ask yourself, what does it take so that when you take the derivative of it, you get 3/2 t squared plus 5. And so here you can see my power of 2 raises to the power of 3. And when I multiply 3 times 3 over 6, I get 3 over 2. Likewise, my integral of 5 is 5t. And again, I have this constant of integration. So I apply my initial conditions. Here they are. At time equals 0, plug in 0 for t. The position is 20 in the x, so that solves for cx is 20. And likewise, here's my velocity equation for the y direction. When I integrate that, I get 2/3 t cubed plus 2t plus c. And I'm going to apply my initial conditions, there they are, and solve for c. And now I have an equation for position in the x as a function of time and position in the y as a function of time. These are the equations that tell me the position at all times t. So the question specifically asked me for what is the position at time equals 4 seconds. So I'm going to take my equations, plug in 4 for t, and come up with my x and my y coordinate for my position at time equals 4 seconds. So when I put that in unit vector notation, here it is, r equals 72i plus 90.7 j. Recall that I and j are just directions only. That's why they're called unit vectors, because they have a magnitude of 1, and they show the x direction for the I and the y direction for the j, and then the coefficient is the magnitude. So 72 in the x, 90.7 in the y. Now that we know where it's located, the next question was, what is its direction of travel? And here is a location of common mistake for students to make. The r vector is described by 72 in the x and 90.7 in the j. All right, so here's my coordinate system. X, y. So there we go. That's my location, right? I would draw the r vector. If I drew it on the paper, it would look like this. That is the vector that represents the location of my particle. At that moment, time equals 4 seconds, that it's at that position, it is moving in a direction that has 29 meters per second in the x direction and 34 meters per second in the y direction. That is what I got when I plugged in my time equals 4 into my velocity equations now. So I plugged time equals 4 into my position equations to come up with these coordinates, but then I take my velocity equation, not my position equation, plug in 4, and I get 29 in the x and 34 meters per second in the y. So now that velocity vector is right here. Okay, so you can see that the velocity vector does not point in the same direction as the position vector. It might, but usually it doesn't. All right? And so they're asking us for the direction of the velocity with respect to the positive x-axis. So here's where I imagine a coordinate system is superimposed right here, and this is my positive x-axis. So in other words, that's the angle right there that I'm looking for. Here's the equation that I was talking, the velocity equations that I plugged in 4 seconds to give me my x and y components of velocity. So now this angle right here is inverse tangent of opposite, which is the same as Vy, over adjacent, which is Vx. So here you can see I've taken my Vy value, my Vx value, and taken the inverse tangent to come up with my direction of travel is 49.5 degrees.